My uncle has a friend that's really into barbecue smoking. He has like 5 smokers, and he says his favorite best smoker is the one he made out of 2 metal barrels. Smokes it like just with charcoal.
You probably does both. So, well, I need to do a charcoal boiler, the heat, and then add in the
I think that's what he does because he has like two. It looks like 4 inch or 6 inch pipe welded connected to. He just throws like a stainless steel grill. And it's the big knees.
I have one like that. They're made out of an old oil drum, and it works pretty great. They're pretty way cheaper than buying one, and they work really well.
Yeah, that's what he was saying. He's like, scrap parts, put it together. It was better than the one I spent like $800 on.
So my family's Cajun, Southern, and I lived and worked in Louisiana. And I don't think that anyone or anything I've eaten in Idaho called barbecue is actually good barbecue.
Yeah.
So I don't eat it anymore. I make my own. And you got to smoke a lot of stuff to get that good barbecue flavor on the meat. So.
They're from Baton Rouge.
Your family?
My wife's family.
Your wife's family. Okay. Yeah, that was where I lived when I worked in Louisiana. I really like Baton Rouge.
Freaking gumbo. Fish fry.
You what?
Would you like about it?
I like the friendlier Southern culture. When I moved here, so there's kind of a cultural norm here where when you invite people over or do something, everyone automatically assumes it's a potluck. So the first thing everyone does is they ask me, oh, okay, we're having people over. What should I bring? And as someone whose family is Southern, the first thing I thought was, are you saying that you don't think I can make enough meal to host you? Like I took it as like a negative response to my hostessing ability, which here that's just like polite and nice. And like I figured that out. But it was just this immediate, like, if you invite people over, like it's to be hospitable. It's to feed them. And then there's another weird thing, which here, if you want to hang out with somebody, they might join you to like get coffee or at a restaurant or whatever, and they might not actually order anything because they've like already eaten. And that's, I think, kind of like a Northwest, Intermountain West culture thing. Whereas if you've eaten and somebody asks you to hang out, like you're going to go eat again in the South. So the food, I think, is also delicious in the South. Gumbo. I love gumbo. Po' boys.
Jambalaya.
Jambalaya.
That's my favorite. Whenever Green makes it, you have jambalaya for like a week. Great.
That's good.
Oh.
Like 2 hours in, that stuff is cast iron pot that's like, I think it's a 10-gallon thing. Every time it's like, you can't just make a little bit, it's the whole thing.
My grandma will start each week by making like 5 pounds of rice. And she puts it in her fridge because the best rice for gumbo is stale rice because then it absorbs all the gumbo as it rehydrates and it's like just better. It's delicious. And so she'll just have that rice sitting in her fridge and her little pot of gumbo that she reheats every day. I do not miss the bugs or humidity though. Idaho's got a better environment, better climate.
The bugs weren't bad at all last year.
Where were you?
Here.
Here. Oh yeah, they're not bad here. How many of you guys were aware that cockroaches fly? Most of you guys? The bugs I hated the worst in Missouri and Louisiana was at night when the street lights are on, the cockroaches, they're no longer crawling in the cracks and gutters. They're flying, and they're flying in like, I don't know, these giant insect herds. And so they'll be on the wall, and if you're walking back, like, from a late night of whatever, and you walk by these walls and you disturb them, they like en masse just fly over you like a curtain of disgusting. And it was like the worst experience to try and walk somewhere at night.
We're pooping on you the whole time.
I'm sure they were. And they make this like clicking noise when they fly. You're a bug guy. You know all about bugs.
Actually, almost all insects have wings, but most of them can't fly. Which is good. Otherwise, they'd be in all kinds of trouble.
I had just never thought of cockroaches flying until they flew over me. All right, guys, make sure you go and do your attendance. Does anybody need me to do it for them? Marcus? As long as you remember to remind me each day.
I think I forgot to do mine this morning when I was late.
You did. I switched it because I knew you were not absent.
Oh, thank you.
You're welcome.
Can you put my attendance today?
Yes. And I'm sorry, remind me your name? Denton, that's right. Anyone else need me to get theirs? Caden? Okay. Okay. So was it Ethan who was asking about the batteries and cells last class? No. I don't remember who was asking, but I was looking today for some information for what we're going to discuss, and I happened to come across the fact that Southern Company, and we're going to look at one of their coal plants that's posted in Moodle, actually has put in some of these batteries, and they are powering with little fuel cells. So they've got a chemical reaction, and their byproducts are water, heat, and energy, which is pretty clean. And then they've just got these little battery cells, and their one station is 25 megawatts, and then their other station was like 2.6. And these are in Delaware, and they're connected to a parking lot, apparently for charging electric cars. So it was kind of interesting because we were talking about it, and then I found an example of some power companies actually trying to step into that battery technology. So it's starting.
Like the fuel cell, is it like a hydrogen cell?
That is, as far as I could tell, what it is, some sort of hydrogen.
Yeah, for
Without
water,
combustion. Yeah.
They're making trucks like that too.
When I was in college, the chemical engineering department had a hydrogen powered vehicle competition that students could do, and they would make hydrogen cells for a little like RC car, and then they'd see how long they could power it without any charging of the battery, and they do like these little competitions. It was very nerdy, but I think it's a similar concept but bigger. But I thought that was cool, so I thought I'd share it.
But what would be like the shelf life of that, huh? How long could it store it?
I don't know. They didn't have, I can post those links I just closed on Moodle if you guys want to read about it. A lot of it is indicating that it's pretty experimental. So they weren't sharing a ton of numbers, but the fact that we're building it and looking, like, I think we're going to know those things and be able to improve on it faster. Okay. to start with watching this video. This is Alabama Power. They are a subsidiary of Southern Company, which has all of coal, nuclear, wind, solar, hydro, natural gas, and battery fuel cells. So as I was looking, I got a lot of questions on the quiz question that asked you to compare power production for coal and nuclear power plants. And some of the questions made me kind of think that maybe I hadn't worded the question very well. So I edited it and hopefully it's a little more clear. But just looking at Southern Company. So here's their solar portfolio. They have this many solar facilities as part of their portfolio. And they range around 20, 100. I think there was one that got up to 300 in this list, but they're relatively small, right? The amount of megawatts they're producing in these facilities. Compared to here, this is just within Alabama. Their hydroelectric plants are 50 megawatts. 1,800 megawatts here at this coal plant. 2,640 megawatts here, getting bigger. 2,370. And their nuclear plants almost 2,000 megawatts, a little bit less, a little smaller than the coal plant. Here, this one, 1,800 megawatts, again, a little smaller than those coal at 24, 26, right? Vogtle, which is a very exciting power plant because the only nuclear unit that's under construction in the United States that's close to operating is being put in here at Vogtle. 2,400 megawatts, getting a little higher, but still, in general, our nuclear plants produce a little bit less than our coal. I think the number in the quiz and from some of the information we were looking at the last lecture put coal plants about 2,900 megawatts, and on average, nuclear plants are closer to 2,000 or just under. So when you're looking at that question, typically, nuclear power plants produce a little bit more. Here again is wind, down by the solar levels of 50 to 200 megawatts, much smaller, and part of why it can't be a good baseload power source. And then natural gas, a little bit smaller, but they can get up to competitive with nuclear in certain plants. So just hopefully that gives you a little bit of clarification on the range of comparison we can have in those power sources. And I just accidentally, I think, closed the video I wanted open. That's okay. Let me share this sound with the folks online. Can you guys online see that video?
Yep, we see it.
Yep.
Plant Miller is a coal-fueled power plant located in Quinton, Alabama, on the Locust Fork branch of the Black Warrior River, about 25 miles northwest of Birmingham. The plant provides over 20% of Alabama Power Company's generating capacity and is the largest generating facility in the state, with a peaking capacity of over 2.9 million kilowatts, or 2,900 megawatts of electricity that can serve over 822,000 homes. Named for Mr. James H. Miller, a former president of Georgia Power Company and senior vice president of Alabama Power, Plant Miller first provided electricity to our customers in 1978, with the most recent unit commissioned in 1991, making Plant Miller the newest coal-fueled power plant in Alabama. At Plant Miller, we use coal, air, and water in an energy conversion process that allows us to deliver electrical power to homes and businesses. Using coal as a fuel source, we generate steam in our boilers. That steam will be used to turn a turbine that ultimately allows us to generate electricity. Of course, there's a lot more to it than that, so let's take a look at how the process works. Our process uses Powder River Basin coal from Wyoming, a subbituminous type coal, as a fuel source. When the coal arrives at our plant by train, we use a trencher and a series of long conveyors to stack coal in our yard, move it to storage silos, or send it directly to the plant. We try to keep a 37-day supply of coal, about 1.4 million tons, on the pile in our coal yard, and up to 40,000 tons in silos. Since we burn as much as 38,000 tons of coal in a 24-hour period, we need to ensure we have a substantial amount on hand. Coal moves into the plant on a conveyor and is stored in a series of silos, each one leading to a feeder, pulverizer, and ultimately to the boiler. At Plant Miller, we have 4 generating units, and each unit has 7 silos feeding into one single boiler. The coal within each silo falls into a feeder, which measures and controls the flow of coal into a pulverizer. Inside the pulverizer, coal falls onto a large rotating bowl, where it is continuously crushed by 3 large grinding wheels until it becomes the consistency of baby powder. Once the coal is a fine powder, it falls off the grinding bowl and is carried by warm primary air, maintained at 140 degrees Fahrenheit inside the pulverizer, to the boiler through 8 burner lines. When the particles of coal reach the burners, they are mixed with secondary air that has been preheated to over 500 degrees to support complete combustion inside the boiler. The combustion of the coal converts its chemical energy into thermal energy, creating a temperature inside the boiler of over 2200 degrees. That's enough to heat the water in the series of boiler tubes to create steam, which moves onto the turbine to power the next step in our process. Superheated steam from the boiler, which is approximately 2400 psi and 1000 degrees, travels to the high-pressure section of the turbine, where it creates the force that turns the turbine shaft. This process causes the steam to lose temperature and pressure, so it must be sent back to the boiler to be reheated to 1000 degrees. After reheating, the steam returns to the intermediate turbine and continues through the crossover into the low-pressure turbines. The force of the steam turns the turbine shaft, which turns the generator rotor at 3600 revolutions per minute. This rotation, along with the induced current on the rotor inside the generator, produces voltage, completing the process of generating electricity. The generator output is 24,000 volts, which is stepped up to as much as 500,000 volts for transmission. Plant Miller uses a closed-loop circulating water system that allows water to be reused over and over. One way we use water is in the condenser, where steam enters from the turbine and condenses back into water as it passes over tubes filled with cool circulating water, which is chlorinated river water from nearby Mulberry Fork of the Warrior River. The condensed water moves into the hot well, where it re-enters the system to be reheated, turned back into steam, and continue its use throughout the plant. Let's take a closer look at the circulating water the plant uses, starting at the cooling tower. Cool water is pumped from the cooling tower basin through large pipes to the condenser to absorb most of the heat from the turbine exhaust steam, leaving us with warmer water that must be cooled. So the warmer water is circulated back to the cooling tower, where it enters through riser lines to the top of the cooling tower fill. As the water cascades down the cooling tower fill material, it's air-cooled, allowing the heat to escape up through the natural draft cooling tower. The cooled water is collected in the cooling tower basin to be recirculated back to the plant to condense more turbine steam exhaust. Once combustion is complete, the heavier particles of ash, called bottom ash, fall into the bottom of the boiler. There, the bottom ash is crushed using clinker grinders, mixed with water and sluiced to the hydro bins, where the water is decanted and ash collected in dump trucks and either sold or moved to on-site storage. While the heavier particles of ash fall to the bottom of the boiler, the hot flue gas containing finer particles of fly ash naturally flows up to the top of the boiler and around, down, and out through the backpass section. The last section of the boiler is the economizer. Because of the shape and the flue gas flow path, some of the fly ash falls out here into hoppers. This economizer ash is pulled by vacuum, mixed and sluiced with water to the ash booster station, where it is moved to on-site storage. Flue gas, a byproduct of combustion, exits the boiler and enters the selective catalytic reducer, or SCR. While entering the SCR, ammonia is injected into the flue gas stream, where it reacts with several catalyst layers to reduce the nitrogen oxide compounds. The flue gas then passes across the air heater, where over 400 degrees of temperature are transferred from the exiting flue gas to preheat the primary and secondary air entering the plant. Next, the flue gas passes through the precipitators, where a negative charge is induced onto the fine particles of ash contained in the flue gas. That ash is then collected with an opposing charged collecting plate. These plates are then shaken by vibrating wrappers, causing the ash to fall off into hoppers at the bottom of the precipitator. The ash is then pulled with a vacuum to a collection facility for sale or storage. The flue gas then passes through the induced draft fans and to the scrubber, where booster fans pull the flue gas from the plant and push it through the scrubber absorber. In the absorber, flue gas mixes with water and limestone. The limestone reacts with and removes about 98% of sulfur dioxide, creating the byproduct of gypsum. The wet flue gas exits out the top of the absorber through to the wet stack, and a gypsum slurry stream is pulled from the bottom of the absorber and sent through a dewatering facility. Inside the dewatering facility, most of the moisture is removed from the gypsum so it can be sold for use in wallboard. When the power leaves the plant, we increase or step up the voltage for transmission purposes to as much as 500,000 volts to help minimize losses from the transmission of power. Our transmission group is responsible for the large transmission lines, towers, and substations that handle the large voltage transfer of power over long distances. Our distribution group interacts with our customers more directly and handles delivery of the power in lower voltages stepped down in substations and delivered to industrial, commercial, and residential customers in various voltages to suit their needs. It is our responsibility to provide our customers with reliable, affordable, and clean energy for their needs, and we take that very seriously. We hope you enjoyed this virtual tour of Plant Miller.
So a lot of these processes, are they using the power that they're making to run the process as well?
Yes. And one of the things that they do really well at coal plants, as you saw that economizer, their waste heat is actually being used to heat the air coming into the plant for combustion. So they're actually very efficient from a design perspective. And then a lot of the power to run the facility comes from the facility itself as well. There's actually a couple stages where you reheat, both going to the turbine with the steam and the air coming into the plant initially, all of which is done with the waste gas in a coal-fired plant, which is, I think, is very elegant of an idea. Okay, we're going to talk a lot next week about each one of those components that they talked a little bit about, economizers and our boiler vessel and our ignition and all of that. So today, we're just going to look at the types of boilers in a little bit more detail. So let me, and these documents that I'm going to be taking from are all posted on Moodle if you want to refer to them. Let's load them. Slowly. Okay. Okay. So boilers can be classified in a lot of different ways, but essentially, whether it's a coal plant, nuclear power plant, other type of steam producing plant, when you talk about boiler, you're going to talk about your feed water, your steam, and the fuel that helps you go from water to steam. Right? In your reading, it talks about the nuclear steam supply system, right? Whether it's a boiler with coal as fuel or it's a boiler vessel and a boiling water reactor, that cycle of producing heat to create steam from water and condensing and cooling and repeating to produce electricity makes up the core function and safety concern at most of your energy producing plants. With coal, you're not as worried about your fuel overheating because you can simply remove the ignition source and you no longer have fuel burning. But you are worried about what happens as that fuel burns, the scale that builds up inside, the quality of your water. Nuclear, you might have a little bit more concerns with how you treat the fuel. And your biggest accident scenario is usually a loss of coolant because you can't shut down a nuclear plant the same way you can coal. But that cycle, that steam supply system, is actually more or less the same in both. You're going to heat it up, make it into good quality steam, put it through a turbine, cool it, and bring it back. So, right, we're going to use a whole bunch of piping and fuel to accomplish that. When we're talking about specifically boilers that do not use nuclear fuel, so our other types of boilers, there's a lot of different ways we can classify them. And some of these types of boilers we're going to really ignore in this class, okay? The biggest set are water tube and fire tube boilers, which is classification about how the water and the hot gas that you've created from burning the fuel interact with each other. In a water tube boiler, you have your hot gas in a tube surrounded by or immersed in flowing water. In a fire tube boiler, sorry, that's the one I just said, right? Hot gas in tubes surrounded by water. Water tube boiler, you've got water in tubes surrounded by hot gas. At Plant Miller, the picture they showed us, was it a water tube or a fire tube boiler? Water tube. Exactly. You can also classify boilers by the water circulation arrangement they use, natural or forced. Most of the time, the heat levels we're getting to and the amount of power that we need to produce at a utility company size plant is not going to be able to rely solely on natural circulation. We need things to move faster. We need more efficiency. We need pumping. And so we're typically going to see water pumps and various other ways of forcing that circulation. Yeah.
What's the power production difference between both?
I do not know offhand the difference, but I do know that this one is significantly larger. I can look and have that next class a number for you. I just don't have, I don't want it memorized. You can also classify boilers by how you use them, right? So marine boilers, they might be fire tube or water tube, but they're going to be specific for use on a ship. And locomotive, these are specially designed for engines like a train. You might use fire tube, might use natural circulation, might use water tube and natural circulation. But when you specifically design them to sit on the front or back of the train, locomotive. We're not really going to talk about these. There's one accident with a marine boiler that we are going to talk about. It's just a really good lessons learned example. Portable boilers, they're mobile and used for temporary uses at various sites. This will actually be more commonly what those of you at a nuclear plant will see, because it's going to be supplementing off-site power. Power plants are going to have stationary boilers. It's designed to be there and produce steam at that plant, not travel on a boat or from site to site. You can arrange the direction of the tubes, whether it's fire tube or water tube, to fit in a certain space. Or to take advantage of certain climate factors that might make some harnessing of some natural circulation a little bit easier. If it's less humid, natural circulation is a little bit more forceful. And so you could take advantage of it in a horizontal arrangement. Sometimes you need that water to stay in the flue glasses longer, and so that you'll make loops and go horizontal. Just kind of depends on the design of the plant. Whether you have any of those arrangements, you can also arrange the position of the furnace that creates heat from the fuel that then heats the water. You can put your furnace inside the shell. Most common type of this is the Lancashire boilers. Or you can put it outside the boiler. You have combustion, and then you transport that hot combustion gas to your boiler shell. Babcock and Wilcox is going to be the most common brand you see of that. They're a huge company in energy production, and they manufacture a lot of components for power plants. You can also have a variety of pressures. Typically, we're going to be at high pressures when we're talking about power plant levels. Okay. Supercritical boilers. These are interesting because they don't use an evaporator. They go to such high pressure the water flashes directly to steam. And this is a little bit less common because the evaporator allows you to operate at lower pressures. There's a lot of energy going into pressurizing things, and there's a lot of maintenance issues when you have things under high pressures, because now you have downtime as you wait for it to depressurize. So you can take things out and work on things, right? So the efficiency you get jumping to this versus using an evaporator, maintenance issues, you just don't see them that often comparatively. Plant Miller talked about pulverized fuel, which is largely the most common thing to do, but you can also have supercharged fuel, which is a little bit more pellet and it's a little bit increased in density when they make the fuel, and then these combustion boilers where you're mixing it more with water to make a fluid. Pulverized fuel is the most common in coal because when you have that baby powder consistency, you make a lot better quality gypsum from your ash products. And that is an income stream for a lot of these utility companies to take their waste and actually resell it as a desirable product. So they've just found that process works best with really fine powder as your input in the first place. It's like the material you use to make like the drywall, sheetrock. It's construction material. The ash is also used as construction material sometimes, like to backfill in holes and things like that. And the ash and fly ash from coal plants is also radioactive. And it is more radioactive than any of the emissions allowed out of a nuclear power plant. Just as a fun fact.
They put it in homes.
Yes, and the United States government got sued because they also used it to build a bunch of schools, elementary schools, on Indian reservations. And then everyone was like, hey, we can't irradiate these children. Is that what you needed, Kyle? Okay. This is also on Moodle, just so you know. You can access it again. We're going to focus in this class mostly on pulverized fuel. We're going to look at the differences between water tube and fire tube, but we're going to focus a little bit more on the water tube. And we're going to, like I said, high pressure and stationary. Those are the classifications that we find more commonly in power plants.
So like blacksmith that was using coal, that exhaust, they're really radioactive.
I volunteer to judge the high school science fair that's held here on campus. And one of the projects last year before, well, I guess a year and a half ago now before COVID, was a girl who got a little radiation detector and she went and walked around Simplot a lot trying to detect radiation from their activities. Because I mean, almost anytime you mine something, you're going to have some natural radioactive component to that because there's just geologically naturally occurring radioactive materials. And it was interesting because with my background, I obviously think that amount of radiation is very much not concerning. But she was like kind of freaking out a little bit in her presentation about how much she detected because it was more than zero. But it's just interesting because a lot of people don't realize they all talk about the radioactive releases from nuclear power plants, but what we are regulated to release is actually less than what coal plants release in their waste. Okay, so let's dive a little bit into fire tube and water tube. Okay. This is the simplest form of the internal furnace, right? So we can classify as internal and external furnace. Right here, we have our fire and our combustion. And then our gases are inside the shell. The combustion process and the flue gases are all inside the shell. And that gas is going to pass over tubes containing water. That's going to heat that water. That water is going to, as it becomes steam, transit to a different system. And then your flue gases are going to head out into their whole cycle as well. Your steam outlet here, right? Fire tube boilers, you get about 25 kilograms per hour, and pressure is limited to about 10 bars. So these are typically lower pressure. That is a reason they're not used as much for commercial power. This one is being shown as a horizontal, but it can be vertical, right? Let's look at water tube, and then I've got one more document where we're going to compare them in a little bit more detail. We're going to take a little bit more time with some of the components of this. Okay. So water tube, this one is a B&W. Okay. So you've got your steam space up here, right? You've got your water tube, and you've got the flue glass moving through, okay? This mud box, as we circulate water through this, after it interacts with that ash, it gets kind of grody. And so some of this water is not going to become steam. It's going to have attached to particles, and they call that mud, and it's going to cycle back down. And that can be cleaned and used again, but it's not 100% of the water going in being mixed with that baby powder fuel ends up going into steam. And that's kind of an important thing to know, is that you've got a little cycle here between the mud drum and the water that comes in mixed with our pulverized fuel. That flue gas then heats around our water tubes, right? We've got superheater here, hopper where it comes in here. And this process of cleaning out the inside of where the flue gases are is something that's a very regular part of maintenance, because you just get a ton of combustion products that stay in that area. And the more that film coats your water tube, coats the inside of your boiler, coats the ignition chambers, the less efficient your system is. What's nice about water tubes is that you can replace these water tubes relatively easily. Got a little list of comparison here, right? Okay, so yes, I can. No problem. Okay, water tube. Water's in tube, flue gases surround it. Fire tube, gases in tubes, and water surrounds it, right? Pretty obvious from the name. We're going to be in higher pressures in the water tube. This is a big reason why that's what we're going to use for our commercial power production. We can get to the necessary pressure to get the efficiency to produce the big amounts of power that we want. The rate of steam generation and the quality of the steam are better. Thinking about that design and just a little tiny bit we talked so far, why do you guys think water tubes are going to generate steam better? You what? Sure, but you're changing from the liquid to the gas inside a fire tube as well, right? It's just
Is it better heat transfer?
it's getting closer to what I'm looking for. What do you mean by that, Jack?
I don't know. I just think that the water would be able to transfer the heat better. I'm sure I could explain that better, but not now.
Yeah.
There's less water, so that instead of having the heat go to big amount of water, it kind of dissipated water.
Yeah, so we're taking the water and we're making it so that flue gas can get around the entire circumference of a small piece of that water. We're essentially breaking the water up into smaller parts and heating the smaller parts faster and getting more steam generation, rather than having a big pool of water and trying to make sure we put our flue gas evenly through all of that pool to heat all of it equally and quickly at the same time. So it does have to do with that heat transfer, but I think your statement is the most correct there. You're breaking the water up into smaller pieces to heat rather than a big tub of water that heat passes through. Load fluctuations are not easy to handle in a fire tube boiler. Once you get your combustion going, you have to get to a certain temperature to create steam from that water to give in pressure, right? So if you want to change how much power you're producing, you only have a small range of temperature change because you have to hit that minimum. Whereas if we want to load follow with our water tube, we can just put a little bit less water through the tubes. That water will still be at the right temperature to become steam. We're still producing electricity, but we could easily produce less and load follow. We talked about Monday the importance of base load versus load following sources, right? This is a big advantage for coal plants. Fire tube boilers are bigger. They're much bigger. And so for the amount of power that you're going to get, you need a lot less space for the water tube systems. Which means if you have a smaller system, it's easier to maintain, it's easier to install, it's easier to add another unit. They are cheaper to transport and install, right? So if you're going to get the same amount of power, choose the smaller piece of machinery to do it with, right? They're also lighter in weight from being smaller and from just the design. It's very difficult to transport a fire tube boiler. Overall efficiency for that fire tube boiler is going to be about 75%. With water tube, if you use an economizer, you can get up to 90%, which is really good efficiency. So you can take a lot of that steam and produce a lot of electricity with very little waste. Part of that, as we look at components next Wednesday, we'll see it's because those coal plants design a lot of efficiency into their boilers by using their waste heat to preheat and treat their incoming air and then to reheat steam from the turbine. Where because in a nuclear power plant, you're dealing with radioactive versus non-radioactive loops, it's a lot harder to do that. So this is a real advantage you can have in a coal system. And specifically, the economizer with a water tube system, which is another of the reasons it's the choice for commercial power production. This one is interesting. Water doesn't circulate in a definite direction, whereas in water tubes, it's going through the tube in a definite direction, right? Having my nuclear background, water doesn't circulate in a very definite direction inside our nuclear pressure vessels. So I'm just kind of used to that being normal. But you can predict the thermodynamic behavior of a system much better if you understand the circulation of a system. So this is a much more well-defined system. It is therefore easier to study. It is therefore easier to design improvements into it. It's therefore easier to predict what behavior you're going to get and create a very narrow margin for what's abnormal behavior. So it's just a little bit more cooperative in terms of doing what you expect, because we can predict what we expect a lot better, which for operation is a definite bonus, right? When we know what the system's going to do, we very easily then know when it's doing something wrong. When a water tube is damaged, it can be easily replaced or repaired. And you don't even have to lose that much production time, because it is possible to not circulate water through a few tubes and still be able to produce power. Whereas it's a lot harder to take out the fire tube, because now you have a tube that has to hold a gas. And whenever you seal a gas versus a liquid, that gas is looking for more ways to get out, right? It's harder to contain it. So when you replace these, you can have more issues with it leaking, which if you're leaking water into your flue glass, you're losing a lot of efficiency. So it's a big negative for operation. And if you can just not have water go through a tube for a little while, you can wait until regular scheduled maintenance and not have to take the system offline in order to make that repair. So it's just a better operational parameter for water tubes. Okay, these are simpler to design and easier to construct. Okay, so even though there's all these advantages and you think, why would anyone ever use a fire tube? They're very simple and they're very easy. And you don't need as high skill from your operators to understand how they work and how to keep them running. These, partially because we're getting to higher pressures, higher temperatures, and higher energy, we just have more risks. You need more skilled operators, more training for going into performing maintenance on these systems. And they're more difficult. And even though The water tube itself is easier. Water treatment is a huge factor for these because you've got to make sure that you don't have buildup of scale or corrosion products inside your water tubes. And so you have to usually put in a whole little miniature chemical treatment plant for your water going in the first place. Whereas here, less of an issue because you're not touching as many surfaces inside each little tube, right? Process industry, commercial power plants. So we will see and study a lot more of the water tube design because it's what's traditionally used in our large utilities power production. Okay. The DOE handbook chapters that I posted start describing a lot of the components and basic operation. I'm not going to go over this in super big detail right now, but I would highly recommend that you guys have at least speed read through this before our class on Wednesday. Remember, there's no classes Monday. Because we're going to talk about a lot of the different pieces in that steam supply system and how they function together. These component explanations right here on page 16 and just 16, these 5 will be very important. I would expect to see questions asking you to describe this similarly on a test. And we'll expand for some of the other components as well. But this is a page I would definitely make sure you understand what it's saying here. And this is posted in Moodle. Any question on water tube boilers, the comparisons we made, or our overview video that we watched? Yeah.
So with that word on the water boiler, you said it gets up to 90%. Where is it without that?
It still beats 75%, but I'm not sure exactly how far it drops it. I think, if I remember, I think they add about 10%. And I know that's in my notes for Wednesday. So we'll answer it specifically on Wednesday. But I think it was about 10%. Anything else? Okay, we'll knock off a couple minutes early then. Any questions online before I stop the video?
All good.
Okay. All right, I will see most of you in a few minutes for capstone.